Hello, the paper presented in this lecture is the result of a joint work with the professors Salas, Rodriguez, and Cigarreta. I'm going to speak about some topological indices, which are a tool that maths offer to measure, or even better, predict some chemical or biological properties of chemical compounds. And I'm going to focus especially in one of those compounds, which are octane isomers, and in one of those indices, the Gutman-Milovanovi index. Chemical graph theory is a branch of mathematics that studied in the 18th century. Here we have possibly two of the fathers of the theory. On the one hand, William Cullen was a Scottish chemist who, since mid-18th century, used what he called affinity diagrams in his lectures in order to represent forces supposedly existing between pairs of molecules in a chemical reaction. On the other hand, Arthur Cayley was probably the first to publish results that consider molecular graphs as early as in 1874. He used this concept for the purposes of enumeration of isomers. Cayley considered diagrams made of points labeled by atoms and connected by links into an assemblage. His collected mathematical papers contain 967 papers. This number has only been exceeded by Euler and Cauchy. A molecular graph, or a chemical graph, is a representation of the structural formula of a chemical compound in terms of graph theory. Graphs are generated from molecules by replacing atoms with vertices and bonds with edges. Usually, we will work with hydrocarbons, that is, organic molecules that only contain carbon and hydrogen. And hydrogen will be suppressed. Thus, the vertices will represent carbon atoms and its edges carbon-carbon bonds. Thus, our graphs will be carbon atom skeletons of organic molecules. A topological index is a single number that represents a chemical structure in graph theoretical terms via the molecular graph, and that correlates with various physical properties, chemical reactivity or biological activity. It's used to understand physicochemical properties of chemical compounds. Topological indices are interesting since they capture some of the properties of a molecule in a single number. To start with, I'm going to speak about Zagreb indices, M1 and M2. The first Zagreb index, as you can see, is defined as the sum of the squares of the degrees of the vertices. And the second Zagreb index is the sum of the product of the degrees of adjacent vertices. They appeared naturally when analyzing the structure dependency of total pi electron energy. However, they are not applicable for modeling physicochemical, pharmacologic, or any other properties of organic molecules. They were proposed exclusively to measure molecular complexity. And here we have an application of these Zagreb indices to two isomers of the same hydrocarbon. In both isomers, we have 4 atoms of carbon and 10 atoms of hydrogen. However, in this configuration, the first Zagreb index has a value of 10, whereas on the second configuration, and this second type of isomer, isobutane, the first Zagreb index has a value of 12. And M2 for the first configuration is 8, M2 for the second configuration is 6. The general or variable first and second Zagreb indices were introduced in 2004. As shown, they just add one parameter alpha to the simple Zagreb indices. But why? Well, when trying to analyze why Zagreb indices proved poor predictions of physicochemical properties in practice, as we said before, chemists argued that in these indices, internal atoms and bonds are more relevant than external ones, as we can see here to the calculations for the index M1 or M2, the inner bonds, inner atoms are playing a relevant role, whereas the external ones are not. Well, however, molecular surfaces generally contribute more decisively to physical, chemical, or biological properties. By incorporating the alpha parameter, now we can make the indices far more versatile. And for example, selecting alpha equal to -1, we obtain descriptors that specifically correct the issue discussed earlier. As we can see, in this case, these indices assign greater weight to exterior atoms and bonds, which significantly improves their ability to model compounds' physicochemical properties. Let's define now a new topological index. The general sum connectivity index, defined this way, was introduced in 2010 and generalizes the first Zagreb index. It serves as a molecular descriptor that captures the branching and connectivity of molecules. Here we have an example of how to calculate, for example, the general sum connectivity index with value 1 for the two isomers that we saw before. It's by correlating the index with biological activities, researchers can use it to screen and optimize potential drug candidates, reducing the need for expensive laboratory testing. The general sum connectivity index is widely used in quantitative structure property relationships, QSPR, and quantitative structure activity relations, QSAR, to predict physicochemical properties such as boiling point, enthalpy of vaporization, entropy, and centric factor, and also biological activities like pharmacological or toxicological properties of some organic compounds, including drug molecules and industrial chemicals. The general sum connectivity index has been applied to the study of nanostructures and other complex molecular systems to model and predict their properties efficiently. And finally, the Gutman-Milovanovi index was introduced in 2020 as a natural generalization of the first Zagreb, the general second Zagreb, and the general sum connectivity indices. For example, when the parameter beta takes the value 0, M alpha 0 is the general second Zagreb index, or when the parameter that is made equal to 0 is the first, M0 beta is the general sum connectivity index. Although its main application is in mathematical chemistry, this natural concept, distance-balanced graphs and related indices, has found uses in network analysis and other areas. It helps in characterizing the connectivity and balance of distances within a network. It's important for understanding robustness, efficiency, and vulnerability of networked systems. In summary, it's a natural concept useful in network analysis and other areas. Here we have an example of a particular choice for alpha and beta, alpha equals 1 and beta equals 2, and the Gutman-Milovanovi index calculated for the two isomers of the compound C4H10. The formula for this isomer is C8H18, which means that we have 8 atoms of carbon, 18 of hydrogen. Graphically, we could represent it this way, or even better this way when the hydrogens are suppressed. This is the isomer N-octane that, as we will see, has important applications. But in general, there are 18 isomers of 18 octane isomers. 18 versions with the same amount of carbon and hydrogen atoms but arranged differently in space. As I said, the simplest and one of the most important ones is precisely the N-octane, the straight chain isomer for octane. For the sake of clarity, hydrogens, as I said before, are usually suppressed. The choice of octane and its isomers as the subject of study is mainly due to their significance in the chemical and petroleum industries, as well as the role in research of fuels and solvents. However, the versatility of octane isomers extends beyond those fields. For example, some are being investigated for their potential in pharmaceutical industry. In particular, the nature of the isomer N-octane makes it ideal to ensure the purity of medications, acting as an essential element for quality control in drug manufacturing and formulation. One of our goals in this paper was to find appropriate models employing Gutman-Milovanovi index with appropriate parameters to predict some physicochemical properties of octane isomers. The procedure that we followed in our modelization is as follows. Firstly, we determined an LOOCVMC value for each appropriate combination of some alpha beta pairs selected. Once the optimal values for alpha and beta have been determined, we constructed linear models of the form C1 M alpha beta plus C2, where this P is the physicochemical property that we are analyzing. The values of the constants C1 and C2 in each case were obtained using the simple linear regression method. And the resulting models, the particular resulting models that we obtained for each of these properties were these ones. The particular properties that we decided to study in this paper were, well, S, that stands for entropy, the DHVAP, that refers to standard enthalpy of vaporization, then the enthalpy of formation, the motor octane number, the eccentric factor, and finally the total surface area. In this figure, we present a plot of the chosen Gutman-Milovanovi indices in the models presented before, M alpha beta for different values of alpha and beta, versus the physicochemical properties of octane isomers, which we have decided to study. Also, we evaluate the performance of the models mentioned before, which are depicted in all these plots as red dashed lines. To finish, I'm going to choose one of the results of the paper in which we relate Gromov hyperbolicity with the Gutman-Milovanovi index. Let's start with a definition. A graph is said to be T hyperbolic, where T is a non-negative constant, if any side in every geodesic triangle is contained in the T neighborhood of the union of the other two sides. And the hyperbolicity constant delta of the graph G is defined as the infimum of the non-negative constants T, such that G, the graph, is T hyperbolic. So we found this relationship between the Gutman-Milovanovi index with parameters alpha and beta and the hyperbolicity constant of the graph G. So we proved that this Gutman-Milovanovi index is bounded from below by the product of the hyperbolicity constant times an explicit constant, which depends obviously on the values alpha and beta, particular for the Milovanovi index we are working with. Alpha, the constant C alpha beta, is an explicit constant. We also proved that nevertheless, a universal upper bound for the Gutman-Milovanovi index in terms of the hyperbolicity constant of the graph cannot be found. The proof is quite technical and we'll leave it for another occasion. And that's all. Thank you very much for listening.